Welcome to the Deep Dive. Today we're digging into some really interesting research, a paper that's tackling something pretty tough in machine learning.
Right.
Creating these realistic 3D human avatars you can actually animate. And get this from just one single 2D picture.
Yeah, it sounds almost too good to be true, doesn't it? The paper's called LHM, Large Animatable Human Reconstruction Model for Single Image to 3D in Seconds.
LHM. Okay. And that title really grabs you in seconds from one
Good.
photo.
That's the headline promise. You know, for years, this whole area, 3D human modeling, animation, it's been complex, really computationally heavy.
Lots of manual work, special scanners maybe.
Often, yeah, or methods that just took ages to compute. This paper introduces LHM, this feed-forward transformer network. The idea is to kind of leapfrog that complexity.
So it's not just a static model, like a 3D statue.
No, that's the key. It's fully animatable. The output uses something called 3D Gaussian splatting, which we can get into. But it means you can pose it, animate it, and it all happens super fast. Seconds, like the title says.
Wow. Okay, so from one snapshot to a sort of digital puppet you can control almost instantly. That is quite a leap.
It really is. It addresses a lot of the bottlenecks we've seen with older methods, things like generalization, the quality of the animation, or just the sheer cost of running the things.
All right, let's unpack the core of it then. What makes LHM tick? What's the big advancement here?
Well, the main achievement is the LHM model. It's this novel transformer architecture designed specifically for this task. Takes a regular RGB image.
Just a standard photo.
Yep, just a standard photo. And it directly outputs this 3D Gaussian splatting representation of the person in the image.
Okay, you mentioned Gaussian splatting. Maybe give us the quick version. I've heard of it, but...
Sure. So it's relatively new compared to, say, polygon meshes. Instead of triangles, think of it as like a cloud of tiny, smart paint splats, or Gaussians.
Okay, like little blobs.
Kind of. Each one has properties: position, color, opacity, rotation, scale. And together, this cloud forms the 3D object. The really cool thing is, this representation is amazing for rendering things super fast, in real time.
So that's where the speed comes from.
Partly, yes. And critically for this paper, it's also really well suited for being deformed and animated. You can manipulate this cloud of Gaussians relatively easily.
Right, so it's not like a rigid sculpture. It's more fluid. This cloud of particles you can move around.
That's a pretty good way to think about it, yeah.
Yeah.
Adaptable. And the kind of secret sauce here is what they call the multimodal body head transformer, or MbHD.
MbHD.
Got it.
Multimodal implies different types of information.
Exactly. It's all about fusion. It starts with a basic 3D human template. They use something called SMPLX. Think of it as a sort of posable digital skeleton or mannequin. That gives the model a baseline understanding of human shape and how joints move.
So like a geometric prior.
Precisely. Geometric priors from SMPLX. Then at the same time, it looks hard at the 2D input image. It uses a powerful pre-trained vision transformer Sapiens 1B, in this case, to pull out visual features. What does the person actually look like? What are they wearing?
Okay, so geometry from one side, appearance from the image on the other.
Right. And the MbHT is the clever bit in the middle that fuses these. It uses attention mechanisms, which transformers are famous for, to intelligently blend the 3D knowledge and the 2D visual details.
So it's like it has the basic mannequin shape, and then it uses the photo to figure out how to dress it, what textures to put where, getting the specifics right.
That's a really good analogy, yeah. And faces are obviously super important for realism, right? They have a specific component for that, too.
Oh, yeah, faces are hard. All those little details.
Definitely. So they developed this thing called head feature pyramid encoding HFPE. Imagine looking at the face in the photo through different zoom levels simultaneously. The HFPE extracts features from the head region at multiple scales, some coarse, some fine, from another vision model, DynOV2 in this case. Then it combines these multi-scale features.
So it gets the overall head shape and the finer details, like around the eyes and mouth.
Exactly. It captures those high-frequency details crucial for making the avatar actually look like the person in the photo. It's like having both a wide view and a close-up view at the same time.
That makes a lot of sense.
Yeah.
Now, you mentioned earlier that getting data is often a bottleneck. How did they train this thing? Do they need like thousands of 3D scanned people?
That's one of the really clever parts they mostly didn't. They used a self-supervised training strategy.
Self-supervised. Meaning it learns without explicit 3D labels.
Pretty much. They trained it on a huge data set of video sequences. The core idea is the model learns by watching people move in videos.
How does that work?
It takes one frame from a video as a sort of reference, the canonical pose. Then it uses the SMPLX model to figure out how the person moved to get to another frame in that same video, the target pose. Then it tries to predict what the person should look like in that target pose based on the canonical view and the motion. It renders its prediction using the Gaussian splatting.
And then compares it to the actual video frame.
Exactly. It compares its rendered prediction to the actual target frame using what are called photometric losses, basically. Do the colors match? Does the shape look right? They use L1 loss, LPIPS for perceptual similarity, and a mask loss.
So it's learning by trying to warp the appearance from one view to another based on the underlying motion.
Precisely. It learns how appearance changes with pose. And crucially, they also add regularization in the canonical space.
Regularization.
Yeah.
Keeping things sensible.
Yeah, basically preventing the model from doing weird things in 3D. They have Gaussian shape regularization, which encourages the Gaussian splats to stay, well, reasonably shaped, not too stretched or flat.
Makes sense.
And positional anchoring, which kind of nudges the Gaussians to stay close to where the initial SMPLX template suggested they should be, keeps everything geometrically coherent.
So it's learning from videos, comparing views, and has these internal checks to make sure the 3D structure stays plausible.
You got it. This whole self-supervised approach lets them leverage massive amounts of easily available 2D video data rather than relying only on those scarce, expensive 3D scans.
That's a really smart way to tackle the data problem. It's learning the rules just by observing.
It's a big shift, yeah. Moving from scarce 3D data to abundant 2D data.
Okay. To really get the significance here, maybe let's zoom out a bit. What's the backstory? How did we get to LHM? What was the journey like in 3D human reconstruction?
Oh, absolutely. It's been a long road. Early days, we relied heavily on these parametric models. Think early versions of SMPL, Skate.
The ones with sliders for body shape and pose?
Kind of, yeah. They use a small set of numbers, parameters to define the overall shape and how it's posed. Useful for control, but, well, they often lack detail. Clothing, individual facial features, they struggled with that.
Right. Good for the basic form, but not capturing you.
Exactly. Then, machine learning really took off. People started training models directly on 3D scan datasets.
Okay, learning from examples.
Right. Predict the 3D shape directly from an image. These methods could capture much more complex geometry, more detail than the purely parametric ones. But
The data problem again.
the data problem, getting high-quality 3D scans, especially rigged scans ready for animation, is really hard and expensive. So the datasets were often limited.
And models trained on limited data don't generalize well.
Bingo! They'd work okay on data similar to the scans, but put in a photo from the wild with weird lighting or complex clothes, and they'd often struggle.
Makes sense. Lab conditions versus the real world.
Exactly. So that bottleneck pushed researchers towards methods that could use 2D data images, videos. We saw more interest in self-supervision, like LHM uses, also generative models trying to sort of imagine the 3D shape.
Hallucinated almost.
In a way, yeah. LHM feels like a convergence of these trends. It's inspired by large reconstruction models that work for, say, static scenes or objects.
Like reconstructing a room from photos.
Right. But LHM adapts those ideas for the specific quirks of humans' articulation, clothing that wrinkles and folds, those crucial face details. It's a tailored approach.
And the choice of Gaussian splatting seems like a key piece of the puzzle here, timing-wise.
Oh, absolutely. The rise of Gaussian splatting has been huge. It just fits so well. Older representations, like meshes, can be tricky to render photorealistically in real time, especially complex ones. And animating them smoothly, deforming them, that's hard too. Implicit functions are another approach, but rendering them quickly can be a challenge.
Whereas Gaussian splatting is faster, easier to animate.
It offers a great balance. It's inherently point-based or splat-based, which makes deformation more straightforward conceptually. And the rendering is incredibly fast and high quality. It hit at the right time to enable something like LHM.
And the transformer architecture, the MbHD, how does that fit in the history?
Transformers have, revolutionized NLP and are huge in vision now. Their strength is understanding context, seeing relationships between distant parts of the input.
Like relating an arm's position to how a shirt should look.
Exactly. The MbHD uses that power to fuse everything, the global look from the image, the local geometry from SMPLX, the fine details from the head features. It lets the model build a coherent 3D understanding by connecting all these different pieces of information.
So LHM isn't just one breakthrough, but more like building on advancements across different areas, data strategies, representations, architectures.
Precisely. It's a smart synthesis of recent progress, focused specifically on this tough problem of animatable humans.
Okay, let's crystallize this.
Yeah.
If someone asks, what's the big deal about LHM? What are the key takeaways, the non-repetitive points?
All right, number one, it hits state-of-the-art performance. Better reconstruction, better animation quality for single-image animatable avatars compared to previous work.
Okay, top quality.
What else? 2, speed. It's fast. Seconds to generate an avatar compared to minutes or even longer for some older optimization-based methods. That's huge for usability.
Seconds versus minutes. Big difference. 3.
3, the multimodal transformer, the MbHD. It effectively combines the geometric knowledge from SMPLX with the visual details from the image, leading to better capture of things like clothing texture and overall appearance.
Smart fusion.
4, the head feature pyramid encoding, HFPE. This specifically targets facial details, making the avatars much more recognizable and preserving the person's identity better.
Tackling the face challenge. 5.
5, training strategy. Using self-supervision on large video datasets avoids the need for massive, hard-to-get 3D rigged datasets. Makes it more scalable, more adaptable to real-world data.
Learning from videos. And lastly,
6, regularization. The canonical space checks ensure the final 3D model is well-behaved, geometrically plausible, animatable without falling apart or looking unnatural.
quality, speed, smart fusion, better faces, scalable training, and stable geometry. That sums it up pretty well, so those are compelling advantages. Thinking beyond the research lab, what does this mean for the real world? Where could we see tech like LHM making an impact?
Oh, the potential is pretty broad. AR and VR are obvious ones, right? Imagine highly personalized, realistic avatars for immersive experiences, making virtual worlds feel much more alive.
Your better avatars would be huge for the metaverse concept.
Definitely. Gaming, too. Faster character creation, maybe even letting players put themselves in the game more easily and realistically.
See on your face, get an animatable character.
Something like that could become much more feasible. Then there's virtual meetings, social media. Imagine having a lifelike digital twin for online interactions. Could make communication feel more natural, more present.
Less like talking to a cartoon character.
Exactly. And for content creators, artists, designers, it could be a massive time saver. Quickly generating a posable 3D human model from just a reference photo, that streamlines workflows significantly.
Telepresence, maybe. Remote collaboration.
Yeah, absolutely. Better digital representations could really enhance that feeling of shared space and presence when you're physically apart. And maybe the biggest thing is accessibility.
How so?
Well, if you don't need specialized 3D scanners or hours of expert modeling work, just a single photo, it really lowers the barrier to entry for creating detailed digital humans. It democratizes it in a way.
It really does feel like we're getting closer to a future where these digital versions of ourselves are much more common, much more realistic. Okay, this is fascinating stuff. And work like this always makes you think, what's next? This brings us to our novel notions segment. Based on LHM, what are some maybe speculative but interesting research directions this could spark?
Right, so thinking beyond what LHM does, what could it lead to? One idea that comes to mind is dynamic detail generation based on animation.
Dynamic details, what do you mean?
So LHM creates a great animatable avatar, right? But the way clothes wrinkle, or maybe how muscles subtly bulge when someone moves, those fine pose-dependent details are mostly driven by the basic skinning from the SMPLX model.
Okay, so it might not capture the exact way that specific shirt wrinkles when you bend your elbow.
Precisely. So the idea would be to extend LHM, or build on top of it, to dynamically generate those details based on the current pose or animation. Imagine wrinkles forming and smoothing out realistically on clothing, or subtle facial microexpressions appearing as the avatar talks.
Whoa. That would be another level of realism entirely. How might someone approach that? Seems hard.
It's definitely challenging. One way could be training a secondary network. Maybe a generative model like a GAN or a diffusion model that learns to predict things like displacement maps or normal maps, basically, textures that add fine surface detail.
Conditioned on the pose.
Yeah, conditioned on the pose parameters coming from the animation controls. So the base LHM avatar provides the shape and appearance, and the secondary network adds the dynamic surface refinement based on how it's moving.
Okay, that's one angle. Any less obvious approaches?
Well, you could maybe leverage temporal information more directly, train a model, perhaps incorporating a temporal transformer, on video sequences. The goal would be to learn the correlation between pose changes over time and how these fine details emerge or disappear.
Learning the physics of wrinkles from video.
Sort of, yeah. Learning the visual consequences of motion, it might be a multi-stage thing. LHM gets the base, then a temporal refinement network looks at the motion sequence and adds the dynamic details. You'd probably look at work in dynamic texture synthesis, maybe even physics-based simulation for inspiration.
And the real-world impact of that.
Yeah.
Even more believable avatars.
Hugely more believable, yeah. For AR/VR, gaming, virtual meetings, it would make interactions much more immersive. Think about digital doubles in movies, too. But there's an overlooked aspect.
What's that?
Richer nonverbal communication? Those subtle shifts, the way fabric moves, it conveys information. We read those cues subconsciously. Adding that layer could make virtual interactions feel much closer to face, of course.
Performance. Rendering all that detail.
Exactly. The computational cost of generating and rendering these dynamic details in real time would be a major hurdle to overcome. Optimization would be key.
That's a really cool direction. Okay, what's another novel notion inspired by LHM?
Another exciting possibility is personalized avatar style transfer.
Style transfer, like applying an artistic style.
It could be artistic, or it could be more literal, like changing the clothing style, the hairstyle, maybe even subtle facial characteristics. The core idea is start with the avatar LHM generates from your photo.
Okay, so it looks like you.
Right. It preserves your identity,
Ah.
but then allow the user to apply a new style, maybe drawn from other reference images or even described using text.
So I could take my LHM avatar and say, make me look like I'm wearing the outfit from this fashion photo, or give me cyberpunk hair.
Exactly. That's the vision. It combines LHM's reconstruction power with techniques from style transfer, text-to-image generation, maybe even few-shot learning, so it can pick up styles from just one or two examples.
How would that work, technically?
The obvious path might be to train a style transfer network that takes the LHM avatar features and the style input, image or text, and modifies the avatar's appearance accordingly.
Okay, makes sense. What about a less obvious angle?
You could explore things like meta-learning. Train a style module that's specifically designed to adapt very quickly to new unseen styles with minimal examples, or maybe part-aware style transfer.
Part-aware.
Yeah, use semantic segmentation to understand which parts are clothes, which are hair, skin, etc. Then you can apply the style more intelligently, like don't try to put a letter texture on the person's skin. Make sure the style transfers consistently across the whole outfit. Diffusion models could also be powerful here, conditioned on the base avatar and the style prompt.
And the impact of that. Total avatar customization.
Pretty much. It could revolutionize how people create and personalize their digital selves. Imagine virtual fashion, trying on clothes digitally that look realistic on your avatar. Personalized gaming characters, much more expressive social media profiles. It lowers the barrier from needing 3D modeling skills to just needing reference images or ideas.
That sounds amazing, but any catches?
Definitely ethical considerations. If you can easily change appearance while preserving identity, the potential for misrepresentation or creating convincing deepfakes increases.
Right, making someone look like they're wearing something they weren't, for example.
Exactly. So ensuring robust identity preservation, making sure it still fundamentally looks like the original person, just styled differently while also being mindful of misuse, that would be absolutely critical. It's a powerful tool and needs careful thought.
Wow. Those are two really thought-provoking directions, dynamic details, and personalized style transfer. It really shows how foundational work like LHM can open up so many new doors.
Absolutely. It's a fantastic step forward, achieving impressive results on a hard problem. And like all good research, it immediately makes you think, okay, what else can we do now?
Well, this has been a fascinating deep dive. LHM really does seem like a significant piece of work in the quest for realistic, accessible, digital humans.
It definitely pushes the field forward. The speed and the single image input are major wins.
For our listeners, if you want to get into the nitty-gritty, we definitely recommend checking out the paper. We'll put a link in the description. It's LHM, Large Animatable Human Reconstruction Model for Single Image to 3D in Seconds. The code is also available on GitHub if you want to explore it further.
Yeah, seeing the visual results really drives home what it can do.
Definitely. So thanks for joining us on the deep dive. It leaves us wondering, as these digital representations become ever more realistic and easy to create, how will they truly integrate into our daily lives? What will that future look like? Something to think about. We'll catch you next time.